Report 3.1 Transmission Layout. Typical systemic diagram from alternating current AC transmission and distribution. Now between the power station and the consumer, there is a large network of electrical conductor can be divided into parts. Number 1, the transmission system. Number 2, distribution system. These main two parts can be subdivided by another two parts. Number 1, primary transmission. Number 2, secondary transmission. And number 1, primary distribution. Number 2, secondary distribution. Related GIS, gas isolated substation. The figure is showing the layout from a typical AC power transmission and distribution system by a single line diagram. Generation station, this is the very first sector for everything, and this is where we produce electricity. There are several power plants can be used to produce electricity like gas fuel power station, nuclear power station, and others. And this figure that provide there is a part called generating station where we can produce electric power by three-phase alternator operating in parallel. Related underground power distribution system. The most common generating voltage is 11 kV, but sometimes 3.3 kV or 6.6 kV are used for industrial competitive power generation. Now come to transmission. For the economy in the transmission of electric power, the generation voltage is stepped up to 132 kV or above by a three-phase power transformer. This type of transformer called a step-up transformer. Secondary transmission, where voltage will drop by step-down power transformer. Primary distribution, for this part, all industrial consumer, those who need bulk power and they can connect with the primary distribution parts, but they will need special permission from the government for special occasion. Secondary distribution, from the sector all 11 kV consumer and 220 voltage single line consumer will get the power. For the 220 voltage distribution system, a transformer 3-phase or single phase will be used for step down from 11 kV 400 voltage or 220 voltage.
Power transmission line support. Line support plays a major role in power transmission. It keeps the proper spacing between the conductors and maintain the conductor at the prescribed distance from its ground parts. It also maintains the specified ground clearance. These clearances are decided by electrical and mechanical consideration. The line support used for transmission and distribution of electric power are of various types, including wooden poles, steel poles, RCC poles, and lattice steel tower.
Hi, I am Jeric Capapas from ELT2A, Group 3, so I will be reporting about the line insulators. The line insulators provide insulation to the power conductor from the ground for overhead transmission lines. The insulators are connected to the cross arm of the supporting structure. The power conductor passes through the insulator clamps. These insulators are composed of either glazed porcelain or toughened glass. The insulators, materials, and configuration are chosen wisely for the best performance and cost of the transmission line. Generally, the insulators are made of porcelain, are silica 20%, feldspar 30%, and clay 50%. The percentage of the material may vary according to the applications. The porcelain used for insulator must be free from air and non-porous. For every 1/10-inch thickness, the dielectric of porcelain should be 15 kV to 17 kV. As porcelain is less affected by temperature, mechanical strong, and has a minimum leakage problem. Therefore, it is suitable for the overhead transmission line. Sometimes toughened glass is also used as an insulator because it has higher dielectric strength 35 kV for 1/10-inch thickness that make it possible to use of single-piece construction, and it is also used for any operating voltage ranges, as the line insulators are exposed to dust, atmosphere, and dirt deposits on the surface of insulators that gradually increase the leakage current of the network. The clearance between two ends of the insulator should be sufficient to avoid breakdown due to leakage current. Creepage distance is known as the shortest distance between two conducting parts along the surface of insulating materials. The properties of insulators. The following properties must have insulators for the best performance in the transmission line. First, to avoid any leakage current, insulators should have high electric resistance. Second, to withstand conductor weight and wind blow, it should have high mechanical strength. Third, it should be free from impurities, void, and cracks. Also, to maintain the dielectric strength, it must be non-porous. Next is, to increase the dielectric strength, it should have high relative permittivity. Next, puncture to flashover ratio must be as high as possible. The type of insulators. There are 4 types of insulators used to overhead transmission line. The pin type, the suspension type, strain type, shackle insulator, guy, stay, strain insulators. Failure of insulators. The below list show the reason of failure of the insulators: porosity, poor mechanical strength, internal impurities, cavities, surface flash over due to dust and dirt, breakdown due to high voltage, aging effect. Porosity. The overhead transmission line, porcelain and stearate insulating material is porous and likely to absorb the moisture. If their surfaces are not properly glazed and smoothened, the resistance of insulating materials will be decreased if it absorbs the moisture, and it will increase the leakage current. The leakage current may damage the insulators and puncture the material permanently. Poor mechanical strength. The insulator loses their desired mechanical strength due to certain design defects. Therefore, due to the weight of the conductor and wind loading, insulator gets broken. Internal impurities, cavities. While manufacturing the insulators, it may consist of certain impurities, cavities, and or voids. The breakdown strength of insulator decrease due to such impurities. Hence, even at the rated voltage, insulator may get damaged permanently. Surface flash over due to dust and dirt. As the line insulator, it's directly in contact with an atmospheric condition. Dust and dirt deposit on its surface. This may cause the flashover between the conducting ends of the insulator. Also, in the rainy season, moisture accumulates on the surface of the insulator that also causes the flashover. It causes permanent conducting tracks on the surface of the insulator. If there were frequent flashover, therefore insulator loses its property. Breakdown due to high voltage. The system voltage increased suddenly due to lightning stroke on transmission line and switching surges. If the rate of rising of surge voltage is more than the welding of dielectric strength, then the breakdown of the insulator occurs that is permanent. And last is aging effect. Continuous use of insulator for a long period causes high leakage current through it and reduction in breakdown strength. That's all.
Grounding. The term ground refers to a conductive body usually the earth grounding, a tool or electrical system means intentional creating and low resistance path to the earth when properly done. Current from a shot or from lightning follows this, thus preventing to build up a voltage that would otherwise result in electrical shock, injury, and even death. There are two kinds of ground. Both are required by the OSA construction. System or service ground. In this type of ground, a wire called the neutral conductor is grounded at the transformers again at the service instance in equipment ground. This is intended to offer enhanced protection to the workers themselves. If a malfunction causes the metal frame of a tool to become energized, the equipment ground provides another path for the current to flow through the tool to the ground. There is one disadvantage to system may occur without the user's knowledge. Using a ground fault circuit interrupter or GFCI is one way to overcoming grounding deficiencies.